Okay, on today's episode of Calc 1, we're going to look at the second derivative and the effects on the function that the second derivative can tell us. So before I do that, I wanted to just shoot back to what we were talking about in class before we left on this extended break, and that was what the first derivative tells us about a function. And we came up with 5 basic points. The first was that when the first derivative is positive, the function is increasing. When the first derivative is negative, the function is decreasing. If the first derivative equal to 0, then that point is called a critical point. If you're at a critical point and the function changes from increasing to decreasing, then that critical point is a relative maximum point. And if you're at a critical point and the function changes from decreasing to increasing, then that critical point is a relative minimum point. And the first function that we looked at was this polynomial here. And to determine where it was increasing and decreasing, we had to take the first derivative, right here, set it equal to 0, go through the process of solving it, and then we made this little sign line, and on the sign line we just tested points to see where the intervals were positive and negative. And we determined that the function was increasing, that the first derivative was positive, so the function was increasing from negative infinity to negative 2, and from 4 to positive infinity, and it was decreasing from negative 2 to negative 4. All right, so what I'm going to look at today is what the second derivative tells us. And if we think about this for a minute here, all right, the second derivative is the derivative of the first derivative. So the second derivative tells us the rate of change of the first derivative. So that is the rate of change of the slope of the tangent line to the curve. So if I were to draw a curve, let's say I draw a curve that's kind of shaped this way. And I'll take 3 points along this curve, there, there, and there. And if I sketch in a tangent line, if I can do this carefully, all right, at each of those points, you will see what the tangent, all right, well, pretend that's tangent. You'll see what's happening to the tangent line, right? As I move up the curve from left to right, the tangent line is getting shallower. So that means the slope of the tangent line is getting less and less. So for example, if this line had a slope of m equals 2, and let's say this line had a slope would be x equals 1, and maybe this is a slope of m equals 1/2, m not x, sorry, m equals 1/2, then you can see here what's happening, right? The slope of the tangent line is decreasing. So if we think of the first derivative as a function, right, the function that represents the slope of the tangent line is decreasing. That means its derivative has to be negative. And the derivative of the slope of the tangent line is the second derivative of the function. So in this case, f double prime, the derivative of the slope of the tangent line to the function, is going to be negative. If I have, say I turn this around, all right, and I have a function now that's kind of going this way, and I'll take 3 points again, right here, and I look at the tangent line to the curve along these 3 points, what I can notice here is that the slope of this line is now increasing. It's getting steeper. So if this was m equals 1/2, this would maybe be like m equals 1, this might be m equals 2. All right, the slope of the tangent line is increasing. And the function that represents the slope of the tangent line is the first derivative. So if the first derivative is increasing, that means its derivative has to be positive. Right? So its derivative would be f double prime of x is going to be positive here. All right, so if we look at these shapes, this shape right here is kind of cupped downward. It has a shape that basically, if I were to put water in it, it would spill water. This is called concave down. All right, over here, this shape has a shape more like this. All right, if I were to put water in it, it would hold the water. That is called concave up. Oop, lost my C. All right, so a function that is kind of cupped downward is called concave down. A function that is cupped upward is called concave up. And the relationship is with the second derivative. A function that's concave down, or has a region that's concave down, has a region where the second derivative is negative. And a function that has a second derivative that is positive is going to be a function that is cupped upward or concave up. All right, so we end up with some definitions here, right? So if f double prime of x is less than 0 on an open interval from a to b, then f prime. F is concave, what did I say? Less than 0, concave down on the open interval from a to b. And if f double prime of x is greater than 0 on the open interval from a to b, then f is concave up on the open interval from a to b. All right, so we get similar definitions to increasing and decreasing, but now describing concavity. Now, there's got to be a place where a function changes, right? If a function changes from concave up to concave down or concave down to concave up. So let's say I have a function that looks like this, right? There's some place right in here, right, where the function changes. It's concave down up to that point, and then after that point, it's concave up. This point right here is called an inflection point. Not infection, inflection. Now, the difference between this and critical points is, remember, we defined a critical point to be any place where the first derivative is 0 or undefined. An inflection point is very specifically a place where the function changes concavity. So they occur when the second derivative is 0, but just because the second derivative is 0 or maybe undefined doesn't necessarily mean you have an inflection point. An inflection point, you have to change concavity. All right, so we're going to define an inflection point, right? An inflection point. I did it again, infection. I've got that on my head right now. Inflection point is a point where the function changes concavity. Okay, now they occur where the second derivative is 0 or undefined. All right, they occur where f double prime is equal to 0 or undefined. All right, but just because you have a place where the second derivative is 0 or undefined doesn't necessarily mean that you have an inflection point. You specifically have to have the second derivative being 0 or undefined, and at that point, the function changes concavity. So if we go back up to our original function from last class, all right, let's take the information that we started with here. All right, we're going to find the second derivative, and we're going to find the point where the second derivative is 0, and we'll see if we have an inflection point, and we'll see where the concavity goes. All right, so we have f prime here, so f double prime is going to be the derivative of this, so that's going to be 6x minus 6. And so if I take 6x minus 6 and I set it equal to 0, this one's easy because it's just a linear equation. So we're going to solve this out. So x is going to be 1. So I'm going to do the same thing I did for the first derivative. I'm going to make this little sign diagram here. So I've got 1 in the middle. Second derivative is 0 there. And I'm going to go back now and I'm going to check. So if I pick a point over here, say I pick 0, 6 times 0 is 0, minus 6 is minus 6, which means it's minus. So it's minus on that whole side. If I pick a point on this side, let's say 2, and I plug it in, 6 times 2 is 12, minus 6 is 6, so that's positive. So that's going to be positive on that side. So that means I can call 1 an inflection point. The function changes concavity, so x equals 1 is an inflection point. Because f changes concavity. At 1, right, at x equals 1. All right, so if I'm going to do like I did over here for increasing and decreasing, the function is concave down on this side, right? So it's concave down. Down from negative infinity up to 1, and it's concave up from 1 to positive infinity. All right, so now I have some information about the function. Now, we're doing this obviously because I'm leading into something that has to do with applications. If this was strictly a math-based Calc 1 class, you know, if you were math majors, I would go on to graphing functions and explaining how this is used to graph functions. I'm going to do that, but again, that's secondary to our purpose. So I'm going to just take a quick look at that, and then I'm going to go on to the other. We did 2 other functions in class last time we met, and I'm going to just run through the second derivative for those. But if you wanted to put this together to get an idea of what the function looks like, all right, let's take a look. I'm going to see if I can squeeze this in here. All right, we're going to try and squeeze this in here. And then I'll show you on the calculator, because I've got the calculator that I can show you what this looks like. All right, so we have 2 critical points. All right, so I'm going to just tick this out here. So at negative 2, and 1, 2, 3, 4, and we have an inflection point at 1. All right, so let's put all this information together to see if I can figure out a rough idea of what this function looks like before I actually show you what it looks like. All right, so my function starts out increasing from negative infinity all the way up to -2. The function is increasing. But notice over here, it's concave down, right? -2 would be over here somewhere, okay? So it's got to be concave down and it's got to be increasing. So concave down and increasing would mean it's coming from up here. It's somewhere up here, it's going to hit -2. All right, at -2, it turns around, right? It hits a maximum point. It turns around, right? And then it starts decreasing again. Okay, and it's going to decrease, but it's also going to stay concave down because it's concave down all the way up to 1. All right, so it's going to turn around here and it's going to start to come back down to someplace here, let's say, and it's going to keep that concave down shape. At 1, it goes from being concave down to being concave up. But notice over here at 1, it's still decreasing. So it's going to change concavity, and it's going to continue to decrease until it gets to 4. And then at 4, it turns around and it starts increasing, and it stays concave up. All right, so it's going to do something like this. All right, and of course, that would continue at both ends. All right, so it's a little wibbly in here, but that's okay. All right, so you get this basic shape. And again, it's a cubic. You should all know what a cubic looks like. All right, so if we take a look at the calculator, all right, and I have to turn my calculator on. All right, you'll see right there what the function looks like. All right, so you can see the shape of it. All right, you can see the shape of it here. It's increasing up to where it hits a maximum at around 2. It turns around, it becomes decreasing, but notice how it stays concave down until somewhere around 1. And then it turns around again, stays concave up, and becomes increasing. Okay, so, whoops, that is not what I wanted to do. Hang on. Let me clear that. Okay. All right, so let's go back to the whiteboard and take a look at the other 2 functions, right? And then we'll talk about some other stuff. All right, so the next function that we looked at was this one. Yep, and that one. Okay, so this was the next one that we looked at. And we had our first derivative here, and at this point we had a point where the function was undefined. All right, so our function was x to the 2/3, so the derivative was 2/3 x to the -1/3, and that turned over into this here. So we had a point where the function was undefined at 0. We tested where it was increasing and decreasing. Okay. So now if I want to check the concavity here, right, f double prime of x, and remember when I go to take the derivative, I want the power function form, so I'm going to use this. So I bring the 1/3 down, and I get -2/9 x to the -1/3 minus 1, so that is going to be -4/3. Right, so that is, again, -2 over 9x to the 4/3. So that this is, again, a point where the second derivative is going to be undefined. Okay, so if I do my line, if x is 0, this is undefined. Okay. Now I have to test my points, right? So if I pick a point over here, say I pick -1. All right, now we got to remember some algebra here. If I put a -1 in here, right? So if I take f double prime of -1, that is going to be -2 over 9 times -1 to the 4/3. Now remember what the 4/3 means. That means we're raising this to the 4th power, then taking the cube root. So if I take negative 1 to the 4th power, I get positive 1. All right, which means the denominator is going to be positive. The numerator is going to be negative. This is going to be less than 0, which means my function is concave down on that side. Or my second derivative is negative on that side. Stick with that for now. If I pick a point on this side, say x equals 1, and I plug that in, so I do f double prime of 1, I get negative 2, 9 times 1 to the 4/3. Well, 1 is positive. Raise that to the 4th power, it stays positive. Take the cube root, it stays positive, so that whole denominator is positive, but the numerator is negative, so again, the whole fraction is negative, which means this side is also negative. So now I am having a function here that does not change concavity. All right, so I can come over here and say x equals 1 is not an inflection point. And why is it not an inflection point? Because f doesn't change concavity. At x equals 1. All right, so 1's not an inflection point. The function doesn't change concavity. There is a point where it's undefined, so if I'm going to write where it's concave down, I want to do it in intervals like I did over here, right? So the function is concave down from negative infinity to 0. At 0, it's undefined. And from 0 to positive infinity. You would use the phrase just like you would for the first derivative by saying, I'm sorry, this one doesn't have that situation. You would say here that it's concave down everywhere, even though technically it's not concave down at 0. It's not defined at 0, but saying it's concave down everywhere is okay. All right, so if we're going to come up with a rough graph of this function, I'm not going to put, well, I can put this one on the calculator, but I don't think I'm going to. Okay, this function is decreasing up to 0, all right, which means it's coming from here and it's coming down to 0, but it's also concave down. So it's coming down to 0, but it's coming down to 0 kind of this way. All right, and then after 0, the function becomes increasing, but it stays concave down, which means on this side it's coming up this way. That side's kind of, I could do better on that side. Let's see if I can do this without erasing too much. Okay. All right, so on this side it's actually going like this. And this is what the function looks like. All right, whoop, what did I do? Put that back. Okay, so, all right, that is what x to the 2/3 looks like as a function. I'll let you put it into your calculator to figure it out. All right, so this was an example of a function that did change from increasing to or from decreasing to increasing, but didn't change concavity. It remained concave down the entire time. If I scroll down a little bit here, this was the third function that we looked at. And remember, I chose this function because we all know what it looks like already. Okay. Which was x to the 3rd. And x to the 3rd turned out to be a function that was increasing everywhere. If I take the second derivative, right, f double prime, all right, I take the derivative of this is going to be 6x. All right, so if I want to know whether or not I have an inflection point, I need to set this equal to 0 and solve it. All right, so that's going to give me x equals 0. Come over here, put 0 on my f double prime line. This was my f prime line. put this on my f double prime line, and I test some values. If I pick a value on this side, say -1, and I plug it into the second derivative, 6 times -1 is -6, which means on this side my function is negative. If I pick a value on this side, say I pick +1, and I plug it in, then I have 6 times 1 is 6, so it's positive on this side. So this does change concavity. All right, so x equals 0 is an inflection point. Right, the function is concave down on the left-hand side, which is -infinity up to 0, and it's concave up from 0 to infinity. All right, and again, we know what this function looks like already. This shouldn't be a surprise to anybody. And in fact, this was the one that we graphed. All right, because what does x cubed look like? I'm going to draw it backwards so I can make it look reasonably like it's supposed to. All right, so here's what x cubed looks like, what we already knew. This function is increasing everywhere because it increases its entire run, and then it starts out concave down, right? So the first part of this is concave down. After 0, it turns around to be concave up. All right, so you can see the relationship between the first and second derivative and what the functions actually look like. Now, again, this is where I would spend a lot of time talking about this if this was a group of math majors. But because we are engineering majors here, I need to talk about how we're going to use this for applications, which is going to be the next video. But we need one more piece of information. All right, let me get some blank space here. Let me go here. All right. And what I'm going to look at is the relationship not between the derivatives and the function, but the derivatives themselves, the first derivative and the second derivative. All right, and this is something called the second derivative test. Second derivative test. And the second derivative test is a way for me to determine whether I have a maximum point or a minimum point with a critical value. All right, so let's take a look. Let's do this visually to start with. Let's take a look at a function that has a maximum and a minimum. All right, and what I want to do is take a look at the relationship between the maximum and minimum and the concavity of the function. So up here, this function has a maximum. And notice that maximums sit on top. And in the case of this, my function is concave down. That's how I get a top. Over here, I have a minimum point, and the minimum point sits at the bottom, and the function is concave up. All right, now, is this true 100% of the time? No, because I could have a function that looked like this, or I could have a function that looked like this. All right, neither one of those fit this profile, but we're not right now interested in that. All right, because this is one of those little theorem definitions that only works in one direction. So let me put a straight x-axis in there. I'm writing off to the side here. Hang on. Okay. So let's put an xy axis in here. This way I can call this point, we'll call this point A, and we'll call this point B. All right, so we notice that F is concave down where A is. All right, so that means that concave down means the second derivative is negative. So that means that F double prime of A is negative. Over here, B sits in a section of the function that's concave up. That means that F double prime of B is going to be positive. And this is going to be our test. So if A is a critical point and f double prime of A is less than 0, that means A has to be sitting at the top. That means it's a maximum point. If B is a critical point and f double prime of B is greater than 0, that means the function's concave up. That means B sits at the bottom. That means B is a minimum. So the first criteria we have for this is the point we have to be looking at has to be a critical point. All right, so let's write out what the second derivative test is over here. So if x equals A is a critical point, of f of x, and f double prime of A is greater than 0, then A is, well, let me write it as x equals A. Then x equals A greater than 0, right, is a relative minimum point. If x equals A is a critical point, and f double prime of A is less than 0, then x equals A is a relative maximum. Okay, that's not right. All right, so there is your first derivative test. Your second derivative test. All right. This is what we're going to be using when we get into the applications next time. All right, so let's go back to the first function that we did. And that was, hang on a second, let me find it. That was the polynomial. Where is it? There it is. All right, so that was the polynomial f of x equals x to the third minus 3x squared minus 24x plus 32. All right, so we had the first two derivatives, f prime of x, 3x squared minus 6x minus 24, and we had two critical values, right? We had the critical values. I'm going to just, you know what, I'm going to start abbreviating this because I'm getting tired of writing it over and over again. Critical values are going to be CV. Critical values where x equals -2 and x equals 4. All right, then we do the second derivative, right, which is 6x minus 6. And now let's use, we already know, right? We already know that -2 is a maximum and 4 is a minimum. We figured that out 2 weeks ago, okay? But let's do this now using the second derivative test, rather than having to go through the whole sine line process. All right, if I take f double prime of -2, I am going to get 6 times -2 minus 6, which is minus 12, minus 6, which is minus 18. That is negative. All right, so if we go back to the second derivative test, x equals -2 is a critical point of my function, and the second derivative is negative at -2. That means -2 is a relative maximum. So that tells me I have a maximum point. If I do the same thing for 4, f double prime of 4, right, then I have 6 times 4 minus 6, which is 24 minus 6, which is positive 18. That is greater than 0. All right, so if I go back to my second derivative test, x equals 4 is a critical point of f, and f double prime of 4 is positive. That means that 4 is a relative minimum point. So that makes this a minimum point. All right, so that's a really quick way of checking whether your critical points are maximum or minimum. And especially if your function is kind of complicated, you might not want to have to factor it to figure out where all the plug in to find out where the first derivative is positive or negative. It may be tricky to do that. So this is a nice, easy way. And once we get into the applications next time, all right, in the next video, you'll see how this works a little bit better. All right, now I'm done for today. So I just wanted to point out to you, let me just find the page in the book. I'm way back here. All right, I think it's page 282. Hang on. Okay. Yeah, page 282 in your textbook, there is a little chart right at the top. And if you're using the online version of the book, it's section 4.2 right at the end, right before the exercises. There's a little chart that gives you information about the signs of the function, the signs of the derivatives, rather, and what each of those means for the function itself. Okay? All right, so by the time I post this video, I'll have a homework assignment for 4.2 posted. And I'll see you in the next video.